All right, first part, quick bell ringer to find the difference between a solid, liquid, and a gas in terms of particle motion. So take a minute, pause the video, take a minute, and write a couple things down. All right, big difference between solid, liquid, and gas in terms of particle motion. Solids move around a fixed point. They vibrate around a fixed point. Liquids can move anywhere inside of a liquid. They can roll or slide over each other, and gases are free to move anywhere inside the container, moving very rapidly. Next, another quick bell ring in the same section of your notebook. Pause the video, take a little time, and come up an explanation of, let's pick out 10 things. 10 things that are wrong. All right, you should have 10 things written down in your notebook under bell ringers for what's wrong. If we look at this diagram, let's start with number 1. They were covering up the first aid poster, can't do that. Number 2, they got too many things plugged into an outlet. You can only have one thing in each slot. You can't have an octopus. 3, oh, there's no fire extinguisher there. 4, you shouldn't be spraying bug spray out. 5, no safety goggles there. 6 is melon right inside the fume hood, not a good place for it. 7, a gas cylinder should be supported at all times. 8, no eating or drinking in the laboratory. See, 9, especially not drinking out of a flask. 10, you shouldn't have your coffee maker hooked up in there. 11, you can't have electric cords all over. 12, pay attention, get your headphones off so you can hear people yell that you're in danger. Let's see, where else are we? 13, where's 13? 13, they got the gas jet on with nothing else hooked up to it, it looks like. 14, you got a messy drawer and open, people are going to trip on that. 15, no smoking, especially on top of toxic flammable drums. 16, take the sunglasses off. 17, don't be stepping over a laser. Let's see, we don't even have lasers that bad, but 18, don't climb it up the side of the wall to get anything. 19, well, you can go on from there. All right, talking about gases here. Big thing about gases, their nature of their gas are influenced by 4 things. First of all, temperature. You always have to have the temperature in Kelvin in order to make calculations. Pressure. Measure in atmospheres, kilopascals. It doesn't matter what you measure your pressure in as long as it's consistent all the time. So in other words, if you're going to measure in atmospheres, you have to always measure in atmospheres. If you need to convert, those are the conversion factors between the 3 major ones. Volume, you can measure in liters or milliliters. Typically, liters are better. And amount of gas is measured in moles. A guy by the name of Robert Boyle came along years ago and looked at the relationship between pressure and volume. Now, in order to look at the relationship between 2 of them, you have to keep the other 2 constant. So temperature and amount have to be held constant if you want to look at the relationship between pressure and volume. What he found was that if you started at initial pressure and a volume and you changed the pressure, the volume went down. And that makes sense. If you take a container and you squeeze on it, the volume will get smaller. That's increasing the pressure. You're going to decrease the volume. This is just a graphic representing that. We have more and more weights being put on it. And as we have more and more weights being put on it, the volume gets smaller, the pressure goes up. Graphically, it looks like this. That is an inverse relationship. Formula-wise, P1 times V1 equals P2 times V2. So as long as you have the same units of pressure and volume on each side, you can plug it into a mathematical equation. Again, this is just another graph of an inverse relationship. So Sample problem, pressure of helium gas in a balloon, volume of 4 at 210 kPa, what would the pressure be at 2.5 liters? Take a second, plug your numbers in, solve it out. Should come up with 340 kilopascals, just simply taking 4 times 210 divided by 2.5 should give you 340 kilopascals. Charles' law deals with volume and temperature. So that means pressure and amount have to be held constant. You can't let any more in. He found that if the temperature went up, the volume should go up. And if the volume goes up, the temperature would go up. They're directly related. And that makes sense. Think about getting in a balloon. You take a balloon outside on a cold day, it gets smaller. Now, tricky thing about this, so we have a direct relationship here. This is how it would set up. V1 over T1 equals V2 over T2. Important thing here, and again, this is a graphic representing that as we heat it up, the volume expands. Important thing is temperature must be in Kelvin. If it's not in Kelvin, then we're going to end up dividing by 0 degrees or have a negative number on the bottom, and that's just not going to be good. Just because you take a balloon from 10 degrees down to 5 degrees doesn't mean it gets cut in half. It's actually going from 283 to 78. That's a much smaller fraction of change. Now, one thing that you can do with Charles' law is if we take some helium, measure its volume and its temperature, cool it down, the volume gets smaller. Cool it down some more, the volume gets smaller. Now, if we keep doing that, eventually the helium will liquefy. But if we extrapolate that line on through, that's one way we have of determining our value of absolute zero. Okay, so volume V1 over T1 equals V2 over T2. Here's our problem. Gas sample at 40 degrees occupies this volume, 2.32 liters. Temperature is increased to 75. What is the final volume? So V1 is 232. T1 is 40, and this is T2. Take a minute, solve that, and then come back again. You should come up with 2.58 liters. Now, important thing is 40 degrees has to be converted to Kelvin. 273 plus 40 is 313. The same thing with 75. Otherwise, it's not going to work. Gay-Lussac comes together with pressure and temperature. So volume and amount must be held constant. He found that there's a direct relationship between temperature and pressure. So again, P1 over T1 equals P2 over T2. If we made a graph, since it's a direct relationship, if we increase the temperature, the pressure should increase also, and it should increase just like that. So again, P1 over T1 and P2 over T2. Here's our sample problem. We have a pressure, temperature goes up, pressure should go up also. Solve that problem through, and come back again. You should come up with 3.6 atmospheres. Since we put in units of atmospheres, we're going to get units of atmospheres out. The important thing, make sure that you convert that to Kelvin. Otherwise, you're going to get the wrong answer. Combined gas law. So we've got gas laws that relate pressure and volume, volume and temperature, pressure and temperature. So if we keep the amount constant, we should be able to combine all three laws into the combined gas law. So this law combines Charles, Boyle's, and the Gay-Lussac law. This problem, 110 kilopascals, 30 degrees, 2 liters, 80 degrees. This is the pressure. What's the new volume? Take a second, pause the video, solve the problem, and then come back. All right, you should come up with 0.58 liters. Again, important part, 30 degrees has to be put in as 303 Kelvin, 80 degrees, 353 Kelvin. You've got to make that conversion. As long as we got both kilopascals here, 110 kilopascals, 440, your answer should come out in liters. All right, work on the problems out of the book and look at pre-labbing Boyle's and Charles' law.